Without warning, in late 2016, a staggering 57 million user and driver records vanished from Uber's internal databases. For years, incidents of this magnitude have been reflexively blamed on highly sophisticated zero-day exploits. The assumption is that to steal data at this scale, an attacker must have bypassed unknown security mechanisms that no one else knew existed. A true zero-day, on the left, uses complex memory corruption bypassing kernel security. On the right, the Uber breach, a plain text AWS key in a code block. No custom malware or unknown vulnerabilities, just a failure in cloud credential hygiene. Clinging to the myth of the unpreventable zero-day actively harms technical education. It allows engineering teams to brush off massive data loss as acts of God, distracting from the reality of misconfiguration vulnerabilities. Studying this specific incident is essential precisely because it required zero advanced hacking. Attackers simply used a valid credential to access the environment through a legitimate portal. Any engineering team could accidentally deploy these exact architectural failures. The attack chain begins in the developer environment. Engineers write code locally and then push those files to a shared GitHub repository for version control and collaboration. The initial access vector was astonishingly simple. Attackers compromised an engineer's GitHub account credentials. In the MITRE attack framework, this is known as Technique T1078, the use of valid accounts. As the login attempt passes the perimeter, notice the critical failure. Uber's GitHub lacked multi-factor authentication. A stolen password was the only barrier. Once inside the private repository, attackers discovered live Amazon Web Services credentials explicitly hard-coded directly into the source code. The developers working on these files bypassed standard secrets management protocols. Instead of referencing environment variables or using an external vault like HashiCorp Vault, they typed live production keys straight into the text. Securing this perimeter requires a mandatory procedural safeguard. Multi-factor authentication must be enforced across all version control systems. It is a non-negotiable prerequisite to stop credential reuse attacks at the first gate. Treating a private code repository as a secure vault for credentials compromises the entire cloud infrastructure from the inside out. A private repository is still accessible by many people, making it a volatile environment for live secrets. With live AWS keys extracted from GitHub, the attackers pivoted directly into Uber's production cloud environment. This raises a critical architectural question. How did one single compromised developer key grant a third party the ability to download the personal data of 57 million people? This map illustrates the AWS IAM policy attached to the stolen key. Notice how access lines connect the key to dozens of sensitive S3 storage buckets rather than isolating it. This is a complete failure of the principle of least privilege. These broad permissions allowed attackers to silently query and download a massive database backup containing names, emails, and phone numbers of 57 million riders worldwide, plus driver's license numbers of 600,000 US-based drivers. Despite the massive volume of data leaving the S3 buckets, the exfiltration triggered zero internal alerts. Uber had not implemented automated S3 access logging or anomaly detection to monitor unusual download patterns. Containing this blast radius requires two strict technical mitigations. First, enforce short-lived, auto-rotating AWS access keys, so a stolen token quickly expires. Second, instrument the cloud environment with logging tools like AWS CloudTrail to detect anomalous API requests. The damage of a lost credential is capped by the permissions assigned to it. Uber's failure to compartmentalize the cloud infrastructure allowed one exposed account to access the entire enterprise. Relying solely on cloud perimeter defense after code is already pushed is an obsolete strategy. Modern engineering requires shifting security left, moving automated checks as early into the development process as possible. The first line of defense is automated secret scanning. Tools like GitGuardian or TruffleHog dynamically detect exposed keys, tokens, or high-entropy strings within repositories before they can be exploited. This diagram of a CI/CD pipeline shows how to intercept human error. When a developer attempts a commit containing a credential, it advances until it hits a pre-commit hook node. The system flags the secret and physically severs the connection. This automated interception prevents the developer from completing the push. They are forced to remove the credential and apply proper secrets management locally before the code leaves their machine. Relying on human vigilance or manual code reviews to catch exposed API keys is statistically guaranteed to fail at scale. Systemic automation is the only mathematically reliable defense against credential leakage. Robust security engineering requires building immutable guardrails directly into the developer workflow, permanently eliminating the root cause of credential exposure by rejecting risky code. The technical misconfigurations enabled the breach, but the profound governance failures that followed turned a security incident into a historic federal crime. The timing of the attack is critical. In November 2016, the Federal Trade Commission was actively investigating Uber regarding a completely separate data breach from 2014. Uber's chief security officer, Joe Sullivan, testified under oath to the FTC about the company's data security practices. Just 10 days after that sworn testimony, he learned of the new 57 million record exfiltration. Faced with a massive new breach during an active investigation, senior leadership actively chose financial cover-up over mandatory legal disclosure. Executives authorized a payment of $100,000 in Bitcoin to the attackers. In exchange, they demanded the hackers sign non-disclosure agreements with false names to guarantee their silence. To process the payment, leadership classified the extortion as a bug bounty. This decision corrupted the integrity of legitimate vulnerability disclosure programs, which exist to reward security researchers, not to launder ransom payments. Technical controls, no matter how advanced, are rendered useless if incident response governance lacks the integrity to accurately classify and report an active extortion event. The public, state regulators, and the 57 million victims were kept completely in the dark. The breach was only disclosed in November 2017, over a full year later, immediately following a change in the company's CEO. The corporate consequences of this cover-up were massive. As seen by the involvement of the Department of Justice, this escalated from a corporate IT incident to a federal enforcement action, resulting in a $148 million settlement forced by 50 U.S. states and federal authorities. But the fallout didn't stop at corporate fines. Joe Sullivan, the executive architect of the cover-up, faced severe personal liability. A landmark legal precedent was established when Sullivan was convicted of obstruction of justice and misprision of a felony. This marked the very first time a corporate chief information security officer faced a criminal conviction for a breach cover-up. In March 2025, the Ninth Circuit Court of Appeals formally affirmed that criminal conviction, cementing this strict standard of executive liability globally. The engineering mandate is clear: vault your secrets, enforce multi-factor authentication everywhere, and build zero-trust pipelines. Relying on perimeter defense alone is a losing strategy. The 2016 Uber incident proves that cybersecurity is no longer just about configuring firewalls. Instead, it mandates uncompromising and immediate regulatory transparency. Because, as the courts have now shown, covering up a misconfiguration can result in a federal criminal conviction.